So last time we stopped after an example on DC bias point analysis. So we went through one problem, which was this first example that was solved in this textbook. And the main idea is what? The main idea is we need to add some DC voltages and resistors around the MOSFET to be able to operate it within the saturation zone. So I need to, the MOSFET by itself, I need to put it in the saturation region. So this is my limits of my saturation region. I need to put it in my saturation region somehow. For me to put it in my saturation region, I need to make sure that I have a certain value of ID and a certain value of VDS. Right? I need to bring it into the saturation region. After bringing it into the saturation region, I want to see now how do I deal with small signal. Because now what I did here, with this I created a certain value of VD, certain value of VS, certain value of VG, all with respect to ground. Right? So, and here we had, so we had VG here at 0 volts, and then we had S here at minus 1.2 volts, and we had D here at, I don't remember, D was at 0.5 volts. Right, so we had the various voltage levels. We know that the difference between these two to operate in saturation is equal to what? Gate voltage is higher than my threshold voltage with an over voltage. Right, so I have a threshold voltage and I have an over voltage. So this is my over voltage sort of here, right? And as long as I'm operating VDS, so this is my drain voltage, as long as VDS is greater than my over voltage, then I'm where? In saturation. Right? So if this is my over voltage here, fine, add it to the source voltage. My drain is higher. And you can always know that as soon as the drain is higher than the gate, we know that we've satisfied the over voltage condition. Since we are already providing an over voltage and the drain is higher than the gate, then we automatically know that I'm already satisfying this over voltage condition that VDS is greater than VOV, right? It's automatic here, right? So we now have placed these the MOSFET into the saturation region. Now we would like to see how we deal with our small signal. What value of small signal can we add? Remember in the diode, what did we do? We had a limit. We had the limit. Our limit was what? Our limit was 5 millivolts across the diode. That came from what? A physical constraint. We said that in our diode case, V over the voltage of the diode over VT has to be smaller than 1. We will have another condition here, where our small signal has to satisfy. We didn't. Here we talked about a large signal, putting it somewhere in the saturation. But where do you put it in the saturation region? Do you put it here? Is this a good place to put? Or do you put it, let's say this is your VDS. Remember VDS?
It's better to put it.
VD is very close to VDD. So maximum value of VD will be, assuming this resistor is not there, for example, then maximum value of VDS will be VDD. Right? So do you put it close to here? You put it close to here? Or do you put it somewhere in the middle?
Somewhere.
Probably somewhere in the middle, because if you're close to here, what happens? If you're close to here and you put a small signal, this small signal you want to amplify it. Amplify it, you're amplifying VDS, right? So if you amplify it and it passes VDD, that's not good, because we know from op-amps and we know from physical circuits, that you cannot get something greater than your power supply voltage from an amplifier, as an output from the amplifier, right? So, okay, do you put it here? If you put it here, you also are limited. You're gonna, if your signal is gonna, too large, it will get into the triode region. If it gets into the triode region, you are no longer in saturation. If you're no longer in saturation, you cannot use the model for the voltage control current source. So the best place to put it is away from this region, somewhere in the middle. So that's what we will talk about mainly today. Okay, so please go through the rest of the examples that are solved. I think they're useful. They all have good ideas. I did not solve, I only solved one for the DC bias point, yeah. And I will solve one also for the small signal analysis, yeah. So, operating the MOSFET as an amplifier is where we're going to talk about, small signal analysis, yeah. Yesterday I also before we wrapped up class, I sort of said that, okay, it's now we have a voltage controlled current source model for our device, our op amp. So this is a current source output that is voltage controlled. So this is my ID, and we have the equation for ID. It's a voltage controlled output, right? Voltage controlled current source. This is my output. This is my source. If I put my source to ground, we said that it's nice. Typically, I would like to create a voltage amplifier. I have a small signal coming from my sensor that is a voltage, for example. I would like to amplify it. So one way to do that is, connect a resistor RD here between your power supply and ground. This will have current ID flowing through it that you are controlling by the gate voltage, right? According to the equations for ID, depending in the saturation mode, right? So, which means it's okay to put a resistor here. It's not a resistor in series that will cause a drop, right? Because I'm pushing a certain fixed current through it ID that I'm controlling, right? So now I would like to take my output. I can take my output across, because again the output ID is proportional to VGS, the gate voltage. I can take my output across RD. We said that's not a convenient way to take output, because typically I would like to take outputs or measure signals with respect to ground. So we said that typically we would take VDS as my output, right? That's the output that we would typically take as when we're creating amplifiers, voltage amplifiers. So what is the relationship between VDS, ID, and RD? It's governed by Kirchhoff voltage law. It's this voltage drop, this voltage source minus the drop across this resistor RD. This resistor RD is called load resistance. It's not really a load, but just it defines. We see that it will define your operating point. It will define your DC operating point. That's why it's called a load resistance. But it's really not a load, because you're going to add an external load later to measure that your signal, you're amplifying a signal. The signal that you're amplifying is VDS. So you're going to take that and you add a load to it. After that, you're going to add your computer, your signal, your analog to digital converter. Remember, all this is still analog. I'm going to take my analog circuits and convert them to digital to put them into the computer. So maybe you have your ADC after that. Maybe you have another circuit, resistive load after that, whatever, right? But that output is across VDS. So, but this is still called the load resistance because it's going to define your operating point here. So, this load resistance again is governed by this relationship, right? So it's this supply voltage minus the voltage drop across the resistance. That would be your output voltage. Right? And now we will define so we showed the characteristic curves for the device before. Now we will define what is called the voltage transfer characteristic. What is the voltage transfer? It's the curves that relate your gate voltage to your output voltage, right? Before, the curves that we showed before were what? ID versus VDS, right? This was the curve that we had before, that we derived the characteristics of the device, ID versus VDS. These were these curves. Correct? This was at different values of overvoltage, 1 overvoltage, 2 overvoltage, 3. This we defined before, and we said, okay, this is the sort of our triode region, then saturation, and then cutoff means current is 0. Right? When is current 0? At VGS is less than VT. Remember, if my gate voltage is less than my threshold, I'm not forming the channel. So I'm in cutoff mode. Correct? When do we get into saturation for a specific value of overvoltage? When my VDS voltage is greater than or equal to the overdrive voltage. Correct? That's when we get into saturation from the triode mode, right? So now this is a curve that relates my current to my voltage. Now remember we said we added this resistor that we had here, right? This resistor, this load resistors now that we added, we called it a load resistance. I would like to now find the relationship between my gate to source voltage and my VDS, which is my drain to source voltage, right? Now I'm creating a voltage amplifier. I want to find the relationship between these two. Find the relationship, it's from here, right? Because this is a specific gate voltage, and then I'm operating at a specific value of current, hence I have a specific value of VDS. But this is not convenient. So I can use this equation that we wrote to define the operating point here. I can use this equation, which is VDS is equal to VDD minus ID times RD. So I can use this equation, and I know the equation for ID, correct? I know the equation for ID in saturation mode. It's what equal to what? It's half Kn VOV squared, or VGS minus VT squared, correct? That's the equation for current in my saturation mode, right? So if I take this ID and substitute in this equation, I now have a relationship between what? VDS and VGS, right? So I will draw that relationship between VDS and VGS. So how do you draw that relationship between VDS and VGS? You draw this relationship this way. So this is VDS and this is VGS. Okay, what's happening? At very low values of gate voltage, right? That is less than threshold, right? What is the device doing? Cut off, right? At very low values of gate voltage. Its device is at cutoff region, right? So regardless of my drain to source voltage, correct? So regardless of my drain to source voltage, it's in cutoff mode. So this is cutoff. This region here is cutoff, right? Regardless of my drain to source voltage. And then what happens? This is VGS equal to VT. Then there's another region, and then a third region.
Is that VOD?
This is VGS, and this is VDS. Okay? So if I start increasing the gate to source voltage, that means I have overdrive, right? If I have overdrive and I start, and my DS, my drain to source voltage is 0, what do I have? I'm pretty much cut off as well. I have gate to source voltage, but I don't have drain to source voltage, so I don't have current flowing. But now let's say I start increasing my drain to source voltage a little bit. What's happening there? And remember, that mode is when my channel width is not being changed, and I have a linear relationship between the current and volt. That's this mode here, right? What is this mode? Triode. So this mode is when I have low VDS, and then VGS higher than VT, right? So it's somewhere, this intersection between this and VGS greater than VT, right? VGS greater than VT. How much greater than VT? Does it really matter? As long as it's greater than VT, I'm creating some overdrive voltage. So let's say I have VGS that's pretty high. Let's say it's somewhere here. And then let's do another point, and then we will see why I will bring that point up here. So in saturation mode, what was happening? I was increasing VDS until I pinched the channel, meaning VDS is greater than VOV, greater than or equal to VOV. So it's, if I have a certain gate voltage, I'm definitely much higher than it, right? If I'm going to be in saturation mode. right? So which means that VDS will be higher than VGS in saturation mode. So if I take this point here, for example, this is a point where I have a high VDS, and I can operate here, or I can operate, let's say, here. If I operate here, VDS and VGS are the same, right? Both of them are pretty high. If this is a linear scale, this is a linear scale. Both of them are high. So this point here is a point where VDS is high and VGS is lower. So this will be saturation. And this will be triode. Okay? What is the maximum value of VDS? From this equation, what's the maximum value of VDS? Assuming RD is very, very small and ID is very small, what's the maximum value of VDS? VDD, right? So maximum value of VDS would be VDD. This is VDD. What is the device doing again in this region? It's cut off. So regardless of my value of VGS, as long as it's less than VT, my device is cut off. If my device is cut off, meaning there's no current flowing. There's no current flowing, VDS is equal to VDD, correct? So my curve looks like this. Okay? At this point, what's happening? VDS is greater than or equal to my overdrive voltage. So I'm in saturation mode. So I can use my equation for current here and substitute and find the relationship between VDS and VGS, right? So here I'm in saturation. I can use my equation now. If I use my equation, I will get something that looks like this. Okay. Yeah, you get something that looks like this because it's because of the form of the quadratic equation. It's a form. It's not a straight line. It would be a quadratic of some form. Yeah. And then this equation, in the triode region, there's also, remember, the quadratic applied all the way to the triode region. But in the triode region, there was an effect on the change of VGS, right? In the saturation region, the equation had no effect on the change of, value of VDS, right? In the saturation region, as soon as the overdrive voltage was greater than, well, as soon as my drain to source voltage was greater than my overdrive voltage, I had an equation for current depending on the gate source voltage only. If you remember from in the triode region, I had an equation for current that depended on not just the gate to source voltage, but also the drain to source voltage, right? So, but it was the same quadratic equation. I mean, you can fit it to the same quadratic equation. A similar quadratic equation, not the same one. So if you go back to the sheet, the summary sheet where we have the equation for current in the triode and saturation, you will find the equation for current. And there you can do the same thing we did here. Basically find the relationship between the gate voltage, the drain voltage, and the drain current. Yeah. And then basically it will look like something like this. Okay? So this is called my voltage transfer characteristic. And it defines the relationship between VDS and VGS. Where did I get VGS? I took this out. This relationship governs this circuit. VDD minus ID times RD is equal to VDS. That's my output that I want. I took RD out from here and substituted with my equation for saturation mode to come up with this curve. And then I took ID out, substituted with the equation for triode mode to get this curve. And then in saturation, the device is cut off, meaning there's no current, meaning VDS is equal to VDD. And that's why it's a straight line here. This curve represents the relationship between VDS and VGS. Here, yes, before we were doing this, ID versus VDS. But remember, we did the DC operating point, right? This DC operating point is for a certain value of ID and for a certain value of VDS, right? Which means I am somewhere here. Again, if you put yourself in, if you made sure that the ID, your VDS and VGS are such that you're in saturation mode, you have brought yourself somewhere here. Somewhere here. Okay? This somewhere here is called your DC operating point, or your DC bias point, or your quiescent point. And we said at the beginning of the lecture today, where do you want to locate that so that you don't, so you maximize the swing of the signal that you have, right? If you're too close to the supply voltage, you will be cut off on the high side. If you're too close to the triode region, you will be cut off on the low side. So you typically want to locate yourself in the middle somewhere. So the value of RD will be what will help you define where you're going to locate yourself here. Because ID, remember, I will take this and substitute it here. So I have a relation between VDS and VGS and RD, right? So for a certain value of VGS and a certain value of VDS, it means I have a certain value of RD.
So
Yes.
for the saturation and triode, it applies to the same equation.
No, not same equation. No, not same equation. I just gave one example. You take this equation and for the saturation region, and then for the triode region, you take the equation for current in the triode region from our table. Right? No, I just gave one example. I didn't write all the equations. Okay, so this is the corresponding curve. We're okay with this?
From here we analyze the small signal.
From here, it's easier to analyze a small signal. Why? Because I'm creating a voltage amplifier. My input is a voltage, and my output is a voltage. Right? So why do this is nice, this is useful, but this is more useful for analyzing small signal. Okay? So, and this comes from this. They're the same. I just substituted with the equation for current to come up with this curve. Yeah. It's easier to work with this when you're during amplifier design. I agree. It's more convenient to work with this when you're talking about your switching, because remember, when I'm switching on and off only, I want to operate only in this region, and then cut off in triode and cut off. So this is not giving me that information readily. How do I know the resistance? Here, you remember, when I'm operating as a switch, when the switch is closed, it's a slope, 1 over the slope. Here, okay, how do I know? I want to know when my switch is closed, I have a certain value of resistance, so I can calculate power loss. Now I don't, but I don't care about this resistance in the case of amplifier operation mode. Now, what I care about is what we were talking about. Where do you place your operating point? Here it was not very clear, okay, where do you place your operating point? It's somewhere, okay? But where do you place your operating point to maximize the gain that your amplifier can provide? We will find that, again, this is VDS versus VGS. So the slope of this line will be the gain. You're putting a signal of VGS. You're getting an output VDS. If you put a small signal here, you want to maximize the value of the output signal, right? You put a small signal here. You want to maximize. How do you maximize? You take the place where you have the highest slope, right? And the place where the highest slope is definitely around the middle here, right? So the slope is going to be the tangent to this line, right? Fine. Looks pretty linear, but fine. It's really not linear, but if it looks pretty linear in this case, and then if you take a point somewhere here, this will be your DC operating point. You can call this your Q or DC operating point or quiescent point. What is a good place to put it? A place where you have the highest slope, and then away from your triode, away from your cutoff, because of what? Away from your cutoff and away from your triode and saturation limits, right? It's not stable, okay? Because again, look at it here. If I put a signal here, if I put a signal here that looks like this, what will the output look like? It will, if this is my VGS, I'm getting a certain value of VDS between this line. This is my VGS, and I get a certain value of VDS between this line. So my signal will look like, a triangular waveform that is centered around the operating point that has this new magnitude, right? Do you see that? If I bring this point Q, so I keep the signal, my input signal, this is my small signal, V, small g, small s, okay? If I keep the same small signal, but I bring Q here, what happens? If I say same small signal, I keep the same small signal, but I bring Q, remember Q was defined by what? Q was defined by your DC operating point, by ID and VDS. By DC operating point, the one we did, the example we did yesterday was your DC operating point. VGS is a small signal on top of your DC. This is your DC point, right? VGS is like, okay, it's like I have, this is my VGS here, and small signal. This is G, capital G, small, capital G, capital S. Then I'm adding a small g, small s in series with it, right? So what are these doing? One is putting the device here, right? This is one of them. This is my big source, my DC source, DC operating point analysis that we did before yesterday. And then this small one is adding a small signal here. This small signal is a voltage above and below your DC operating point. Obviously, I mean, if this is a DC value, this is a small signal, an AC signal, for example, above and below your DC operating point. So your DC operating points really define where you operate, right? And then your small signal is on top of that. Now, if I keep the small signal the same, but I bring my DC operating point here, fine, I have this is a linear here on top, but here I'm starting to hit what? Starting to hit the triode region, which means I will get distortion in my signal. Linear means if I put something, I will get something that looks exactly the same shape, no distortion. But if I put a curve here, this value will be changed with respect to, in magnitude, with respect to the smaller value, for example. Right? So if I operate close to the triode region, I get distortion. But I get a signal. How about if I operate close to my saturation here, close to this point? If I operate close to this point, what's happening? Here, I'm cut off. The current, there's no more current. I'm cut off. I will clip my voltage. My signal will be clipped at this point. So I will get what? Here I will get my negative will be fine. So this is, let's say if I have the same swing, if we have the same swing, my maximum swing, remember, is my power supply voltage. So I will do this, I will have this, and then this will be clipped. Then I will have my negative. This will be clipped. Then I will have my negative. This will be clipped. Then I will have my negative. And then if I operate close to the triode, I don't want to attempt. The top will be fine. Okay? The top will look like a triangle. Then the bottom will be distorted. I don't know, I'm not an artist yet, but it will be distorted. It's not going to be a triangle anymore. Top will be a triangle, bottom will be distorted. Here, bottom will be fine, top will be cut off. Okay, so you see now where the benefit of the usefulness of the DC operating point that we did yesterday? Okay, so now hopefully that's clear. So now we can do this both ways. We can do this graphically, or we can do this same as diode. We can do this graphically, or we can do this with equations, and that's what we'll start doing. And then we can do it all together, DC operating point and AC small signal, or we can split them. If we split them, then we utilize superposition. Superposition means everything in my DC operating point, the sources I will make 0. I will I will short them. So my VDD will be 0. And my capital VGS will be 0. I will only be left with small VGS. Right? And that will be a small signal input to a model. So you can, there are many ways. And then the stuff that we will not cover is, elaborations on that. Elaborations on after we split, elaborations on that. Okay, so now that this is clear, hopefully. let's move on. So we discussed, so we talked about the voltage transfer characteristic. Hopefully it's clear. And this is coming from substituting with the value of the equation for ID current in the saturation mode. And then you can of course solve, if you want to solve for the value of VGS at point B. How do you solve for value of VGS at point B? You put VGS at point B instead of VGS. And then VDS is at point B is VDS at point B is equal to what? Is equal to VGS at point B minus the threshold voltage. So we know VDS is equal to VGS minus VT, because the limit between the saturation and triode is the over voltage value. So V over voltage is equal to the gate to source minus the threshold. So what is the drain to source voltage at the limit between saturation and triode? It's over voltage. Over voltage is VGS minus VT, right? So if you want to find this point, you can make these substitutions, right? Huh?
Bonus, we find this point.
No, you found here. You want to derive it?
Bonus.
Fine, bonus, yeah, fine. Bonus, both, do both VGS B and find VDS C for bonus. This is a point, right? This point here, this canvas, desktop background, clear. So this is one point, right? And they found that for you here. So find this, substitute and find this form, okay? And then this is one point. This is another point. This is VDS C, right? VDS C has a value. What is this value? Okay. In one of the examples they ask you. In this example they ask you to find it. Yeah. So fine, for bonus, find these two points in terms of the parameters, and then solve this exercise.
To define VDS
C.
C,
Yeah.
we just plug in VDD for VDS, and that's it.
Exactly. But I wanted to find it in terms of, for the bonus, for it to be worth the bonus, find it in terms of the rest of the parameters. Find, bonus is not, if you don't want to do it, you don't do it. You don't have to. Okay? But they're all from the curve. They're all substitute. Okay, substitute with this, substitute with that. So okay. Okay, so here is what we talked about, the idea of operating point, and okay, here I don't have my small signal, I just have my large signal, my DC operating. This is what we did last time. For a certain value of VGS, VDS, and VDD, we were able to find the operating point, which defines where VDS is, VGS is, and ID is, right? That's from yesterday's example, but here we put it on the voltage transfer characteristic instead of just solving for it and not knowing why that is useful, right? So they talk about that here, which we discussed, and then they talk about, okay, now we want to look at small signal. How do you add a small? So we add a small signal that's going to be in series with my DC source, DC bias point, or DC operating point. What is the gain of that small signal? The gain of the small signal, it's from this. This is my voltage transfer characteristic. The gain of the small signal, if you add a small signal around this capital VGS, it will be amplified based on this slope. So the slope of this transfer characteristic in this zone around the operating point is what defines your gain. So it's the gain, it's the slope of the voltage transfer characteristic at capital V at V capital DS. Right? So it's a slope at the operating point. So that's what they talk about here. It's the slope of this curve at the operating point. Operating point is capital VGS or capital VDS. Q is the operating point that you have defined from what we did yesterday in the example yesterday, the DC operating point. The DC operating point is what, again,
So the slope at Q is the gain.
The slope at Q is the gain for the small signal. Right? There's no gain for the DC operating point. You're just setting the operating point at a certain place. Right? Now you want to add a small signal. So how does that behave? You have calculated VDS based on putting a certain value of R here or R here or R or on a certain voltage here. Based on the three voltage levels, for drain, source, and gate, you have defined Q, like yesterday's example. And then today, the addition is, okay, we drew the transfer characteristic and we drew Q on the transfer characteristic. And now we want to see the effect of small signal. We looked at it graphically, and hopefully it was clear. And we just said that there are limits on where to put it, right? How do you calculate this? This gain, again, the gain is the slope of this curve. The curve is this equation. It's defined by this equation, right? So this is the VDS, VGS relation defining this curve. So I know that this equation is valid when?
Saturation.
In saturation, between A and B. This equation is valid. So I will differentiate that with respect to differentiate VDS with respect to VGS, and at a certain value of VGS. So after the differentiation, I will put my capital VGS value that I have, and that will to get the slope at the operating point. Because if you just differentiate this with respect to VGS, you have the slope of this curve between A and B. Which points that you want, you substitute with your capital VGS value that you have. Okay, so the slope is equal to this. It's in terms of VGS and RD. So then you will substitute in terms of, you substitute your VGS and substitute with your RD and your VT, and that's your gain for your small signal. Okay, and that's this exercise that we went through. So I went to this graphically, and we said that fine. We located this operating point here, and we went through this, and we said that if we bring this up, if we bring Q up, I will be cut off because I cannot get a voltage at the output greater than my supply voltage. No, that's exactly in the middle. It just has to be somewhere far away from A, far away from B. Because if you're close to A, you are cut off. You're cut off. Your signal will be cut off. If you're close to B, your top will be cut off. Here, if you're close to B, your bottom will be distorted. It would not be a triangular anymore. It would be maybe something like this. Right? So we see? So we have to locate it away. Where do you locate it depends on how much gain you want. If I have just a small signal, if my signal, or if all I care about for VDS, for the output VDS is something that's like this, then it's okay. I mean, I can locate it here, for example. It's okay. I still have enough swing area. Yeah, it depends on how much swing you require. How much swing you require for your signal. Okay, so. Okay, but well, I skipped one thing also. One thing that we should note is this is negative. When we did the differentiation, this was negative. So what does that mean for my output voltage versus my input? It will be 180 degrees out of phase, right? So that's one thing I skipped. So if you see here, that's your input is one way, and then the output is flipped. So the first half cycle is positive, negative, negative, positive. They're 180 degrees out of phase with each other. Okay. So again, where we locate this depends on how much gain you require and the amount of swing that you have. They just talk about the 180-degree phase shift and the fact that the gain is proportional to the load resistance. So the value of RD comes up in the gain here. Right, so it's something that it's one of the design parameters and that's we found from the DC operating point. I mean, it's one of the remember from the DC operating, the example that we did yesterday. What did we do? We added an RD here without calling it RD. We just said there's a resistor. I call it RD, but we didn't understand what the value of this RD was. But what this RD did was what? Put us somewhere. It put us somewhere. It created for a certain value of ID. It created a certain value of VDS for a given VGS, right? We were given a voltage with respect of the gate, and then we had a circuit. This circuit defined what? This circuit defined the value of source voltage with respect to minus 2.5, and the drain voltage with respect to minus 2.5, or with respect to ground. Sorry, it doesn't matter, right? So this circuit that we added is what defined. If I change RD, is it going to change the values that we got yesterday? Yes, it will. Change RD, it will change.
Didn't we add RD to control the voltage?
Yes, you added RD to control the value of the drain voltage and the source voltage.
That's why if we like change.
Sure, but we didn't understand the value of it, right? So yesterday we put it there, we did some analysis, but we didn't understand the value. So hopefully today, by looking at the gain equation, you see that it affects significantly the gain. So it affects the gain, and it also affects the place of the operating point. So it affects the gain of the small signal. It also affects the operating point, because the operating point is also defined by the resistors that we added around the device, right? So they're just summarizing that here. And then, okay, so they took what they did also was take the gain equation, which is minus Km VOV times the RD, and then they substituted with VOV. Remember, we know that the overdrive voltage, the drain current, is equal to half Kn times VOV squared, right? In saturation, VOV is VGS minus VT, right? Right. So this is the equation for drain current in the saturation mode. So now I would like to maybe write. I will take the overdrive voltage out from this equation and write my gain in terms of my DC operating point. Right. So just to see it's another equation to write, another form of the gain equation. So I substituted with what I know is my DC operating point, my ID from my DC operating point analysis gives me a certain overdrive voltages. I would write my gain in terms of my DC operating point. And then this gain will have a maximum value. What is this maximum value? This maximum value, we know that IDRD can take a maximum value of what? IDRD from the equation of VDD equals VDS equals VDD minus RDID. This, if VDS is 0, right, I get RDID equals VDD. That's the maximum value of RDID. So which tells you that's the maximum value that you can plug in here, corresponding to the maximum value of gain that you can get. Right? Okay? If they're just saying maximum, what's the maximum value of this gain? But this is the value equation for gain. There's nothing. What is the maximum value? This maximum value occurs when VDS is equal to 0. But we know that if VDS is equal to 0, I don't have current flowing anyway, right? Right? But they're just trying to. It's a manipulation of the equations here. Okay, so now we'll do an example. Yeah, we'll do an example there. So we have an amplifier circuit here, where amplifier circuit 529A, 529. Yeah, this amplifier circuit. So we have a DC source in series with a small signal, and we have my load resistance here, and I want to look at my output voltage. So this is our basic amplifier configuration here. So what is the question? Consider amplifier circuit. Transistor is specified to have, so they're giving you VT, and they're giving you Kn prime, they're giving W over L, they're giving you lambda is equal to 0, so you're neglecting channel length modulation. They're giving you a certain supply voltage, a certain value of load resistance, certain value of gate to source voltage, right? Part A, they're telling you, okay, there's no small signal, which means what? I'm doing my DC operating point analysis, like yesterday. Right? For part A, it's DC operating point analysis. So from my DC operating point analysis, I look at my circuit. My circuit looks like what? I forget about my small signal. I only have my large signal, VGS. I have my MOSFET, and I have my RD, and I have my VDD, and my source is connected to ground. My objective is to calculate what I'm giving RD. I think we want to calculate ID and VDS, right? Yeah, ID, VDS, and the overdrive voltage and the gain at this operating point, right? Because we said that the DC operating point will show me where I am on this curve. Where I am on this curve will define the slope, which means will define the gain. Where I am on this curve will, and the gate voltage that I have will define how much overdrive I have, and from my characteristics I will be able to calculate, ID and VDS. I will be able to, if I know ID, I can find what value of VDS I have. Yes, ma'am.
When they ask for AV, do we get the maximum value?
No, they want the voltage gain at this operating point.
What's the point of the AV max?
They're just, it's the maximum value of gain that you can, theoretical maximum value of gain that you can get from an amplifier depending on the components around it. It tells you that the gain is controlled, is really limited by the power supply voltage, the maximum gains power supply voltage, and what? What does it tell you? And the overdrive. So how much gate you have is going to define gain, and how much, and what's your peak value of supply voltage. It's nothing. I mean, it's just a manipulation of the equations. Yeah. So it's good for, yeah. They summarize the okay. They say that here. Okay, for a certain overdrive voltage, it's a technology dependent thing. So for example, for CMOS technologies, VOV is usually no lower than 0.2 volt, with the result that the maximum achievable gain is 10 times VDD. So if VOV is 0.2 volts, then what is the gain? So it's a technology dependent. Remember, overdrive voltage is the voltage above threshold. So, okay, if the overdrive voltage has to be at least 0.2 volts for you to start creating a channel in a certain technology, then it's, okay, if you want to use CMOS technology, you are limited in gain to 10 times your supply voltage, for example. That's what they're saying. So it's nothing, it's a technology limit, basically, discussion. Okay, so anyway, so back to our example here. So we have our, I erased the MOSFET. So our MOSFET, our VGS, capital VGS, source is ground, RD, VDD, and this is my ID. Okay. Find VOV, ID, VDS, and AV. Okay, so they, with VGS is 0.6, so they gave us the gate to source voltage, and they gave us my threshold. So I know that the overdrive voltage is equal to what? The gate to source minus my VT, right? That you're given. Why is this important? Because this is going to define the boundary. Remember, to go into saturation, VDS has to be greater than or equal to overdrive, right? That's the limit on the saturation, getting into the saturation mode. So we have to make sure that is going to be satisfied. After we solve this, right? This is now VDS. I have to make sure that this is going to be greater than my overdrive voltage. So what is ID? ID is defined by, in my half, remember, half Kn VOV squared. Yeah, that's in saturation mode. We assume we're in saturation mode, right? If we assume we're in saturation mode, then ID is half, Kn is 0.4, right? And then 10 is what? 10 is W over L. So it's Kn times W over L. I forgot. It's either Kn or Kn prime W over L. No. Yes, because it's Kn or Kn. Kn is what we have in the equation before. But remember, Kn was your transconductance parameter, was equal to Kn prime W over L. That was, they grouped this into Kn. Okay. They just called it that. No, it's not the same. Kn is equal to Kn prime W over L. Because all of this is a design dependent parameter. Yeah, they give you Kn prime, and they give you W. All of this is given. This is given. The only thing that you calculated now was your overdrive voltage, 0.2 squared. So ID is equal to 0.08 milliamp. after you know ID, right, you can try to calculate VDS from what? VDD, which is given as 1.8, 1.8 minus 0.08 times the resistance. Resistance 17.5 kilo ohms, given as well, right? So you can calculate VDS. Now, were you correct in assuming that you are in saturation mode?
It's bigger than,
It's bigger than overdrive.
yes.
So it's correct. So our assumption was correct. So we are okay. So we are in the saturation mode. Okay. So we calculated VOV, ID, VDS. Okay, the voltage gain. We will calculate the voltage gain from the equation for voltage gain that was given in the previous, in the previous discussion. Minus Kn times VOV times RD. Right. Everything here we know. We know Kn. We know VOV. We know RD now. Right. So we can calculate the voltage gain. The voltage gain is minus 14 volts per volt. That's it's 14 volts gain. 14 multiple. The gain is 14. It's dimensionless. It's volts over volts. Yeah, right. Like we did in chapter 2. Okay. So now what is the requirement in? So everything in A is done. Part B. What is the maximum symmetrical swing allowed at the drain? Right. So here we have already defined the DC operating point. Right. This part A defined the DC operating point, which means I'm somewhere on my voltage transfer characteristic. I have somewhere on my voltage transfer, I'm somewhere here. Okay, I am somewhere already. I've defined that by part A. If I am here, we said that if my signal is going to swing beyond a certain value, I'm going to enter into triode. So if I am here, if my signal swings beyond a certain value, I will enter into cutoff, right? So I don't want to enter cutoff, I don't want to enter triode. So where did this operating point stuff put me, right? I will have to take all these values and draw this voltage transfer characteristic, right? So if I draw this voltage transfer characteristic now, based on the values that we've calculated, let me draw it in here because it's going to be useful to. Okay, I will draw it here. So my voltage transfer characteristic now looks like this, right? This is VDS and this is VGS. I was given VT. VT was given as what? You have your books. What's VT? This is cutoff, right?
There's 0.4.
Exactly. So this is 0.4 volts. This is equal to VT, right? So I've defined my line for cutoff. Also, I know that is the maximum value of VDS according to, remember, my circuit looks like this, right? So this is my circuit. This is VDS. If I'm in cutoff,
Maximum is VDD.
maximum is VDD, exactly. Maximum is VDD. How about the maximum value of VGS? The maximum value of VGS also, VDD as well, right? So I will not have my supply voltage is this. I will not be able to put a signal higher than my supply voltage, otherwise it's useless. Yeah. So this is VDD as well, my maximum value of VGS. Now I need to define some points. Where is the limit between saturation and triode? For which value of VDS? VDS has to be greater than or equal to the overdrive voltage, so that I'm at the limit between saturation and triode, right? So VDS, I will go, some value here is going to be overdrive. Overdrive we calculated it as what? 0.4, right? 0.2, 0.2, right?
Yeah.
So 0.2 is this point here, and then this is going to define my limit at somewhere intersecting this point is the point where my gate voltage this is going to define what? Saturation here, and this is going to define triode. So This is 0.2 volts. This is VOV. This is my overdrive voltage. This one? This represents the region where I start going into triode mode. Right? So at some point, at some value for VGS, I will start going into triode mode. Right? So let's, and then what we can do is we can draw the characteristics that we have from our equations. We can draw this. Remember, we were able to calculate, given the equation, we were able to calculate the point B. Remember, VGS B was calculated for us. If you go back to this point, VGS B. Yes, the VGS B point is this point that is gonna be at the zone, the intersection between the triode and the saturation region. This point VDS B happens where VDS equal to the overdrive voltage. So what is this point equal to? We have to look at our parameters. This VGSP, the gate voltage here corresponding to this point, is all dependent on everything that we were given. Right? We were given RD, we have KN, we have VDD, right? So we can calculate, and we have my threshold voltage, right? So I can calculate VGSB. I can calculate VGSB, and I know that the corresponding VDS is my overdrive voltage. So this point is defined. We agree that this point is defined by the parameters given in our example. Okay? So now this point has been defined by the parameters given in our example. And so this point is defined. I have my overdrive voltage, so I can define the corresponding gate voltage from this VGSB that I have. Okay. Now what are they telling us? They're asking us for, I think, the maximum swing that your signal can have. Okay. What was the VDS that we calculated? Sorry, can you tell me? What was the VDS? We calculated with VDS was 0.4, right? So VDS now, this is now, I drew my characteristic, right? Here, it's VDD. Here, it's my overdrive voltage. And then the corresponding VGSB from the equation for VGSB that we have, VGSB, right, that we have from a few pages ago. I defined this point. So now I have this point, this curve, and I can draw this curve if needed, but I will not be operating here anyway, right? But you can draw this curve, just draw the extension here. Okay. Yeah, that's like the some point, yeah. Until here, there will be some value here. I don't know the value. The value here is your bonus as well, right? That's the V. This is the VDSC point that you're asked to calculate as bonus. Okay. But again, it's not going to be very important for us because we're trying to operate only in saturation mode. Now I look at my VDS. My VDS is 0.4. VDS is 0.4. Is it above 0.2? Yes. So I am in saturation mode. So I am going to be somewhere here. This is 0.4 volts. This is my capital VDS. So this is defining my Q. This is my DC operating point. Now they're asking us, what is the maximum allowable swing? Right? What's the, because I don't want to go back. What's the question they're asking you? What is the maximum allowable swing, right? What's the maximum allowable swing? The maximum allowable swing is, okay, this is my operating point. The maximum allowable swing will be defined by, okay, if I move into my triode, I've lost. If I move into cutoff, I've lost, which means that it will be defined by this distance here. Right? This is my DC operating point. How much below my DC operating point can I operate without distorting my signal, either by shape distortion or clipping? And this is going to be, since I'm close to the triode region, then it's going to be the distortion issue that I will have issues with. So I don't want to go below VOV. VDS is equal to VOV. So which means that my negative portion of my signal can only be 0.2 volts. And if I have a symmetrical signal, if I have an AC signal that's symmetrical, that means my positive is also going to be 0.2. So I'm limited to a swing of plus minus 0.2 volts because of my DC operating point. Yes, ma'am.
Are we always allowed the overdrive voltage swing? Because this is the value.
No, no. This is minimum. This, yeah, you're allowed to go all the way. If your operating point was here, if your operating point was here, Q, okay, you're allowed all of this on the negative side, but you're only allowed this on the positive side, right?
So for it to be symmetric, then it has to be less.
For it to be symmetric, it's good to be located between your overdrive voltage and VDD. Halfway between overdrive voltage and VDD for you to get your maximum swing, if you want to call it. Is that going to be your maximum gain? It may not be maximum gain. You may get maximum swing, but not maximum gain, right? Yes, ma'am. Yeah, I'm just saying if I change my Q to this, it's not, I didn't change. Which one? This one? This is your DC operating point, correct? Since this is my DC operating point and they're telling me you have a symmetric signal at the input. This is your DC operating point. And you have a symmetric signal at the input. What is gonna limit the swing of the signal? Because now you want to see what is the maximum signal that you can put in. Okay? The maximum signal that you can put in will be amplified. This amplification, we calculated the gain to be 14, right? We calculated, so we know that the gain, and this curve is pretty much linear. So we calculate this gain to be 14. I know that the gain will be 14. So what is my signal limit? What is the limit on, can I increase my signal to 1 volt and get 14 volt at the output? We don't know. What is the limit? The limit is, you go to your operating point. And then your signal at the output will be amplified. This is your output, VDS. It will be amplified around your operating point. So it will be amplified this way and this way, around your operating point. How much around your operating point? Okay, depends on where your operating point is located. If your operating point is located close to this point, VGS, B point, that's pushing the device into triode, then the limit is going to be defined by this part, this area, this length here. The positive side is not limited actually here. The positive side is limited all the way to here. So if you have a signal that is not symmetrical, it's okay. If you have a signal that has much higher positive than negative, you can operate. You will not, no problem. But they're saying if you have a symmetrical signal, what is the maximum peak value of the signal? It's limited by the distance between your operating point and the overvoltage in this case. So it will always be either limited by the operating point value and your overvoltage, or your operating point value and your supply. Right? Because if you're close to here, to be limited by your supply on one side, and overvoltage and difference between operating point and overvoltage on the other side. Right? These are the limits here. So if these are the limits, then what? So now, so we said that the limit will be 0.2, because otherwise you're going to get into the maximum allowable negative signal swing is 0.2 volts. In the positive direction, a swing of 0.2 would not cause the transistor to cut off, because we're far away from the cutoff region. Right? So positive, no problem. Negative, we were limited by 0.2. Thus, the maximum signal swing would be allowable to be plus minus 0.2 volts, which is what we were saying. So if I have 0.2 volts plus minus on my output, what is the maximum value of signal input I can put? Your output divided by your gain. Right? Output divided by gain. So your maximum small signal can have a peak value of 14.2 millivolts in this case. So if your sensor is going to provide something greater than that, then you're going to be distorting the signal. Right? So, or in other words, what they're saying is that the small signal should be significantly less than the overdrive voltage. That's right? My small signal that I had here, if this is my overdrive voltage, my small signal, anywhere I add it, any operating point I have, if my small signal, VGS, is considerably less than my overdrive voltage, then I'm fine, I'm always safe. Because we said that the limit is always my overdrive voltage on the bottom side. Right? So so that's just something that's additional piece of information. What do they do here? Here they're just manipulating the equation. So they're looking at. So after we did this, we can now draw, a certain input and a certain output. So for a certain input signal, that is defined by what? Plus minus 14.2 millivolts, right? This is VGS max plus minus 14.2 millivolts. This is my output signal. Note that it is what? 180 degrees out of phase because of the negative sign on the gain, right? And here they put, what do they put? They put, to try to calculate what the minimum or maximum value of the signal. Greater insight into the allowable signal swing can be obtained by examining the signal waveforms. That's what we just did, looking at the waveform. To remain in saturation at a negative peak, we must have VDS. We must ensure that the minimum value of VDS is greater than the, of course, the threshold voltage, the over voltage, right? That's what we were talking about. The minimum value of VDS should always be greater than the threshold voltage. So they calculated the corresponding value of minimum value for VGS, sorry, from the equation. What? No, they didn't ask this. They were just asking about what is the maximum symmetrical signal allowed at the drain.
Find the maximum allowable.
Amplitude of the signal. No, that's we did that. The maximum allowable amplitude is 14.2 millivolts above my DC operating point. Right? My DC operating point GS was a certain value. I can go 14.2 millivolts above that. Okay, so that's yes, ma'am.
Why did you divide by the gain?
Because you have your input multiplied by the gain is the output. So if you have your output divided by the gain, it's your input, right? Okay. I know it's time. Okay, this is graphically we're not concerned. So graphically, I can do the same by if I take my circuit VDD equals VDS is equal to VDD minus IDRD. I can rewrite that in this form, and this is basically the equation for this straight line. The insight we get here is, okay, where does this Q we found on the voltage transfer characteristic? Where is this Q on the ID versus VDS characteristic? We can get it from this load line. Graphically, we said that we want to stay away from B, we want to stay away from A, right? In the voltage transfer characteristic, we want to stay away from getting into triode, we want to stay away from cutoff. So it's nice, this is nicely located. So they show another example here. This is for a very certain value of RD, another value of RD. Remember, this slope of this line is dependent on RD. The slope of this line is minus 1 over RD, right? So RD really defines this point, this line. So it's going to define your ability to operate. So RD is defined for a value of RD, we get this. For another value of RD, we get this. For a specific value of VGS. So I have a certain gate voltage. Given a certain gate voltage, if you change your RD, you're either on this line or this line. This is not good and this is not good because this one is close to triode and this one is brings this point close to cutoff. So it's nice to have something around here. For this gate voltage, I would like to operate around this point. Okay? Exactly. So the importance of the circuit around the device, right? Which is the resistance in this case. Right? But it can be more than one resistance, right? It can be more than one resistance, like the example we did yesterday.
Yeah.
Right? So it can be more than one resistance. That's why graphically, I prefer to do the mathematical method that we did. Yeah. Okay, so we did small signal. I was really hoping we can go into. If you'd like, I can record this next. I wanted to continue this. Until just this page, until here. Just until here. If you want, I don't mind recording this alone and sending and uploading it as well. If you're okay with this, I will do that because then it gives you more examples to play with. And you're okay with it? Okay. So I will record. So after this class, I will record in my office another class, not a full class, just a few more pages so that we can get to these examples. Because with these examples, then there's a lot of material that you can use to study. Okay, so we'll stop here.